In this video, I'm going to be explaining how cane sugar, also known as table sugar, also known by its chemical name as sucrose, is converted into glucose and fructose when you put it in water. So, this is sucrose, which is made up of a glucose molecule bound to a fructose molecule. Specifically, I'm going to mention stereochemistry because I talked about it in my presentation. It's not super important, but I talked about it in my presentation, so I'm going to let you guys know about it. This is Alpha-D-Glucose and Beta-D-Fructose. There's going to be about 50-50 mix of alpha and beta, but they're all going to be D sugars. So what happens when we put it in water? Well, the first thing is a proton will be attacked by one of these carbons. And when I say attacked, let me explain. So when oxygen is bound to a carbon, or most things really, they don't share electron characters equally. This bond is them sharing 2 electrons. But oxygen is more electronegative, also known as electron-loving than carbon. So it's going to share unequally. And the reason that you know that oxygen is more electron-loving is because it's further to the right on the periodic table. Something like fluorine is even more electronegative than oxygen. So it would share even more unequally if it was bound to carbon. And if you remember from the presentation, atoms with 4 things on it have tetrahedral structure. So let's say this is oxygen in the middle here, and it's bound to a carbon here and here. The electron pairs are going to be on one side. If you draw a line right here, you can see positively charged on this side, negatively charged on this side. And when you have a concentration of negative charge, that's going to be ideal for attracting, so you have concentrated negative charge, that is going to want to bond to positive charge. This is called a nucleophilic attack. This lone electron pair is going to attack this hydrogen. Nucleophilic means nucleus loving, also known as positive charge loving. And if you remember from the presentation, that's how we defined a Lewis base. A Lewis base is an electron donor. So which oxygen on this is the best Lewis base? So we got 2 types. We have alcohols, which are these OH groups. So it's bound to a carbon and it's bound to a hydrogen. And then we have ethers, which is an oxygen bound to 2 carbons. I'll spare you the details, but ethers are much better Lewis bases. And there are 3 ethers on here, and this is the best Lewis base of all 3 of them. So this proton, this H+, is going to be attacked and bind to this oxygen. So you may be wondering, H+, isn't this water? Well, water is going to have a mix of H+ and OH- always in solution. It's just, and it's going to be going back and forth between H2O, H3O+, OH-, H+. Like this is constantly happening. And if you remember, we defined acidity as concentration of H+. But there is, even at a neutral pH, there's still a certain amount of H+ in solution. Even at a basic pH, there's still an amount of H+ in solution. For the purposes of this reaction, we're going to have H+ starting the reaction. However, we could also have OH- starting the reaction. This is known as acid catalyzed, and if OH- started the reaction, that would be known as base catalyzed. But this doesn't have to happen at acidic pH or at basic pH. In fact, if this was very acidic, it would probably cause a bunch of side reactions. We really want maybe a slightly acidic or slightly neutral pH to make this happen. But you're just putting it in water. This is not an acidic solution. So now that we have the hydrogen bonded to the oxygen, that's going to give oxygen a positive charge. Well, how do we know that? Well, once again, we go to the periodic table. Oxygen, which has 8 protons, that's the definition of oxygen, is in column 6, which means it has 6 valence electrons. So if you just take a normal carbon, it's going to have 1, 2, 3, 4, 5, 6 electrons in its outer shell, its valence shell. And everything in the same column as oxygen also has 6 valence electrons. So to determine charge, we take the number of valence electrons, subtract the number of lone electrons, and then subtract the number of electrons that are in a bond and divide it by 2. That is 6 minus 5 equals +1. So it has a +1 charge. And by the way, this is also very crucial to how elements behave. This way of calculating charge is very important. So we have a positive charge on oxygen. It doesn't like to have a positive charge. Oxygen doesn't like to have a positive charge. So it wants to get rid of, now it is more likely to break one of these bonds. It becomes a little easier for one of these bonds to be broken. However, a second thing happens because of this positive charge. These carbons right here, that are one away, that are bonded to the oxygen, become even more positively charged because, remember, they're already slightly positively charged because oxygen is withdrawing electron character away from them. Now they're even more because of the positive charge in the oxygen, which makes them the perfect target for a nucleophilic attack by water. However, you may notice if water nucleophilically attacks here, there's going to be 1, 2, 3, 4, 5 bonds. Carbon absolutely does not want to have 5 bonds. It super unstable. So it's going to kick off this oxygen, which already slightly wanted to leave. And that is going to yield a glucose molecule and a fructose molecule. This is the hydrogen from, this is the hydrogen molecule from the H+. This is OH from water. It's originally going to be, there's going to be H2O here, but like I said, positive charge, it's going to kick off this hydrogen almost immediately. It doesn't want to have positive charge there. And our net reaction, so we've added 1 proton, we've added water, and we've kicked off an H+. We added H2O. So our net equation is sucrose plus H2O becomes glucose and fructose. And this is going to be highly favored to go this way. We don't need a enzyme to try and push this reaction. This is extremely favored. One, because it's in sucrose is in water. Water is highly represented in solution, and the increased number of reactants is going to favor the products. The amount of water is going to favor the products. We don't want to when you have glucose and fructose in solution, it is not going to go this way, because you would have to be producing water, and you're not going to produce this. If this happened, it would be called dehydration synthesis. You're not going to dehydrate glucose and fructose into sucrose while it's submerged in water. It's going to go this way. It's not reversible. It's just going to extremely favor the products. All the sucrose is going to be dissolved. So this reaction is called hydrolysis, which is where you add water to hydrolyze, so separate two things, break a bond. And something you will notice is that the stereochemistry is preserved. So this is not super important, but alpha-D-glucose and beta-D-fructose, their bonds are preserved. However, anomers, which is the alpha and the beta, anomers interconvert in solution. So if you remember from my presentation, I drew glucose as a line rather than a circle because mostly just to show off the stereochemistry, but they interconvert between these two. It mostly favors the ring structure, but they interconvert in solution. And so if it goes to a line, let's say you start with linear glucose. This oxygen is going to attack this anomeric carbon right here, and it can either attack from above or below. It can attack from here or from here. It can attack from here, or if we're saying that this is the carbonyl carbon and that if this is the carbonyl and this is, yeah, if this is the carbonyl carbon, this is the carbon that's bonded to the rest of it, it can attack from here or it can attack from here. And you're gonna get a mixture of alpha and beta. So that's why I drew, this with alpha D and beta D, because there's just a mix of alpha and beta. And that's what you're gonna get. You're gonna get a mix of alpha and beta. But the D is preserved, and originally it is preserved, but once it stays in solution for a while, you're gonna get about 25% alpha D glucose, 25% beta D glucose, 25% alpha-D-fructose, 25% beta-D-fructose. And yeah, that is how sucrose, when you put it in water, becomes glucose and fructose. And of course, this is what high fructose corn syrup is. So anytime you put cane sugar in water, it becomes the exact same thing that high fructose corn syrup is. In the next video, I'm going to explain how high fructose corn syrup is made, because corn syrup is pure glucose. But pure glucose just doesn't taste as sweet. It doesn't taste like sugar. And so to try and mimic the taste of sucrose, high fructose, so in order to mimic the taste of cane sugar, they convert 50% of the glucose into fructose. So yeah, that is how cane sugar gets dissolved into glucose and fructose when you add it to water.